Before I begin today, I thought I'll take the first 5 minutes and show you some fun stuff I've been hacking on for the past 3 years. This has to do with 6002 and circuits and all that stuff, but this is completely optional. This is for fun. This is to go build your intuition. This is to check your answers, whatever you want, okay? So this is not a required part of the course, just for fun. So there is this URL out here that I put down here. So I've been hacking on this system for the past 3 years. And for the first time this year, I'm very tentatively and gingerly introducing it to students. So the idea here is that it is a, that's kind of defocused. Any chance of focusing that a little bit better? Okay, so the idea of this is that it's a web-based interactive simulation package that I pulled together. And what you can do is you can pull up a bunch of circuits. So notice that the URL is up here. It's url.lcs.mit.edu/websim. And there's a pointer to it. So you have a bunch of fun things you can play with. And we've gone through all of these things in lecture. So let's pick a MOSFET amplifier, right? So you come to this page. So this is something you've seen in class. And let's say you want to play with this little circuit. So you can set up, can you see the mouse? Good. So you can set up a bunch of parameters. You can set up the MOSFET parameters, KT, or rather VT and K. You can set up the value of R for your resistor. You can establish a bias voltage, and you can have a input voltage Vin. Okay, so you can apply a bunch of input voltages. Okay, you can apply zero input, unit impulse, unit steps, sine waves, square waves, or this was the part that took me the longest to get right. You can also input a bunch of music, and so far I just have 2 clips, so you're going to get bored listening to them. Good. So you can also input music. And what you can do is you can watch the waveforms, you can listen to the output, and do a bunch of fun stuff. So one experiment I'd love for you guys to try out, again, remember, this is completely optional, okay, just for fun. So you can apply some input, step input, for example, to an RLC circuit, and spend 30 seconds thinking about what should the output look like. I divine that the output should look like Blech, okay? And then do this and see if what you thought was correct. And it's fun to kind of play around with it. So let me start by, just as an example, let's say input classical music. And let us say I would like to listen to the output here. That's the voltage at the drain terminal of the MOSFET. Okay? So default says that, for listening, it sets up a default time for you to listen to. So go ahead and do it. Okay, this shows you the time domain waveform of a clip of the music, and then you can listen to it. Lots of distortion, right? So as you can see, there's a bunch of distortion, and that's as you expect because the peak-to-peak voltage is 1 volt. The bias is 2.5, and so this is clipping at the lower end, plus the MOSFET is nonlinear. Okay, so you can play around with a bunch of things, and you can have a lot of fun. And the reason I created this is that MIT is looking to, is putting a bunch of its courses on the web. And one of the hardest things about courses like this is the lab component. How do you get people, if you're beaming a course to, say, a third world country or something, how do you get people to set up the massive lab infrastructure? I know you hate your oscilloscopes. I know you hate your wires. I know you hate the clips. But the fact is you have it. You have them. And a lot of places, those are way too expensive to pull together. And which is why I've been creating this web-based kind of interactive laboratory so that people can learn this stuff over the web. So let's go do another example very quickly. Let's say you learned about, let's do RC circuits. Okay? So here's the parallel RC circuit. And you can set up capacitor values, resistor values. You can set up input. So here, let me look at the time domain waveform for the voltage across the capacitor. And this time around, let me play a unit step. Okay? and let's see what the output is going to look like. So you can think in your minds what should the output look like, and then you can go and plot it. There you go. That's what the output looks like. Okay? So you can play around with it and have fun. So that's all the good news. The bad news is that so far, I just have one Pentium 3 machine behind this. It's a Linux box, okay? So don't all of you try it at once. However, what I've also done, and that took me another 6 months of hacking in the small amount of time professors have to hack on stuff. I've also hacked an incredibly elaborate caching system so that once anyone in class tries out some combination of parameters, it goes and squirrels away all the outputs. So if anybody else types in the same sets of parameters, it'll just squirrel the output and play it back to you. So, if enough of you play with it over time, we may end up caching all the important waveforms and music clips and all of that stuff. I have allocated a few gigabytes of storage, so I'm hoping that it may work. So, go forth, play with it, and this is completely my fault. So if there are any bugs or anything, simply email them to me. And the first time this is coming alive, so bear with it. Okay. Now let me switch back to our scheduled presentation for today. Yeah. All right, hope and pray that this works. Okay, yes, good. So I'm going to do today's lecture using view graphs. And the reason I'm going to do that and not do my usual Blackboard presentation, which I way prefer to a view graph presentation, the only reason I'm going to do this for today, and maybe one more lecture, is that there's just a huge amount of math grunge in this lecture. Okay? So what I want to do is kind of blast through that, but you will have it all in the notes that you have, so that you don't waste time in class as you watch me, stumbling over twiddles and tildes and all that stuff. Okay. So so the key thing here is that the insight is actually very simple. If you the beginning and the end are connected very tightly and very simple. There's a bunch of math grunge in the middle that we are going to work through, and it again follows a complete old established pattern. So in that sense, there is really nothing dramatically new in there. Okay, so let me spend the next 5 minutes reviewing for you how we got here. Okay, what have we covered so far, and set up the presentation. So the first 10 view graphs are going to blast through and just tell you where we are in terms of LC and RLC circuits. Okay. So I began by, so I showed you this little demo. 2 inverters, one driving, I can model the inductance here with a little inductor, the capacitor of the gate here. And recall that when I wanted to speed this up by introducing a 50 ohm, a smaller resistance, I got some really strange behavior. Oh, just to remind you, for Tuesday's lecture, it would help if you quickly reviewed the appendix on complex algebra in the course notes. Okay, remember all the real and imaginary, J omega stuff? So it'd be good to very quickly skim through that. It's a couple pages. Okay, so so remember this demo, and the relevant circuit that is of interest to us is this one here. It's the resistor, there's an inductor, and there is a capacitor. This is page 3. I'm just going to blast through the first 10 view graphs. It's all old stuff. Then we observe the following output. Okay, we apply this input at VA, and we got this output, a very slowly rising waveform because of the RC transient. And because of that, you saw a delay. Okay, notice that this delay was because of the slowly rising transient. this waveform took some time to hit the threshold of the neighboring transistor. So we said, aha, let's try to speed this sucker up by reducing the resistance in the collector of the first inverter. And so I had this input. And now, to my surprise, instead of seeing a nice little, much faster transitioning circuit, well, I did see a much faster transitioning circuit, but I got all this strange behavior on the output that I was interested in. And because of that, if these excursions were low enough, I could actually trigger the output and get a whole bunch of false ones here because of these negative excursions, which should not really be there. Okay, so that was kind of strange. So in the last lecture, we said, let's take this one step at a time. Let's not jump into a RLC circuit. Let's go step by step. Let's start with an LC, understand the behavior. So we started off with an LC circuit of this sort, and we showed that using the node equation, we showed that this was the equation that governed the behavior of this circuit. And then we said that for a step input and for zero initial conditions, that's the zero state response, let's find out what the output, the voltage across the capacitor looks like. Okay? And so we obtained the total solution to be this. And there was a sinusoidal term in there. And the omega naught, which was 1 by square root of LC. Okay? So and this was a circuit. And so for this step input, notice that the output looked like this. Okay, so for an input step, I had an output that went like this. Notice that it is indeed possible for the output voltage to actually go above the input value, VI. Okay? This is kind of non-intuitive, but this can happen. So this waveform jumps up and down, but on average, its value, the steady state value, on average, if you will, is VI. But on the other hand, it does have sinusoidal excursions, and this kind of goes on because there is nothing to dissipate the energy inside that circuit. So, by the way, the fact that the capacitor voltage shoots above the input voltage is actually a very important property. Okay, we won't dwell on it in 6002, but just squirrel that away in your brain somewhere. I promise you, sometime in your life, you will have to create a little design somewhere that will need a higher voltage than your DC input. Okay? And you can use this primitive fact to actually produce a voltage that's higher than you're given, a DC voltage higher than you're given, okay? And then use that somehow. In fact, there's a whole research area of what are called DC to DC converters, voltage converters. Okay? Let's say you have a 1.5 volt battery, a AA battery, but let's say a circuit needs 1.8 volts. Okay, the Pentium 3s, for example, needed 1.8 volts. Okay, but the strong arm is another chip that required 1.8 volts a few years ago, but the AA cell was 1.5 volts. How do you get 1.8 from 1.5? Well, you have to step it up somehow. And this basic principle where the voltage can jump up above the input is actually used, of course, with additional circuitry to kind of get higher voltages. Okay, it's a really key point that you can squirrel away. Okay, so this was pretty much where we got to in the last lecture. Okay, so this starts off the material for today. So what we're going to do is take that same circuit, but instead we're going to put in this little resistor here. Okay, this is what we set out to analyze. Okay, and for details you can read the course notes section 13.6. So this was the green curve here was the behavior of the LC circuit, and what we're going to show today is that the moment we introduce R, this sinusoid here gets damped. It kind of loses energy, and I'm going to show you that the behavior is going to look like this. By introducing R, this guy doesn't keep oscillating forever. Rather, it begins to oscillate and then kind of loses energy and kind of gets tired and settles down at VI. Okay? And remember the demo. This is exactly what you saw in the demo. You had a step input, and bzz, you have this funny behavior, and for the RLC, that's exactly what it was. Okay, so today's lecture will close the loop on what you saw in the demo and the weird behavior, and I'm going to show you the mathematics foundations for that today. Okay, so let's go ahead and analyze the RLC circuit. So, and I'm going to follow, I've purposely created the entire presentation to follow as closely as possible both the discussion of the RC networks and the LC networks so that the math is all the same, okay? Exactly the same steps in the mathematics or in the exposition of the analysis. What's different are the results because the circuit is different. Okay, so don't get bogged down or whatever in the mathematics. Just remember, it's the same set of steps that you're going to be applying. Okay, so we start by writing down the element rules for our elements. Nothing new here. So for the inductor, it is LDI, V is LDI dt. And the integral form, which is simply 1 by L integral VL dt equals I. Okay, we've seen this the last time. And for the capacitor, the current through the capacitor is simply C dV dt. Okay, those are the two element rules for the capacitor and inductor. The element rule for the resistor, of course, is V is equal to IR, you know that. And for the voltage source, we know that too, the voltage is a constant. Okay, so I just follow the same established pattern. By the way, just so you are aware, I have booby-trapped the presentation a little bit to prevent you from falling asleep. You see the dashed lines here? Whenever you see a dashed line, that stuff needs to be copied down. Haha. Okay? So don't trip over that. Don't say I didn't warn you. Okay, so we start by using the usual node method. And I have two nodes in this case. Unlike the LC circuits, I have two unknown nodes. One is this node here with the node voltage VA. And the second node is the node with voltage VT. So let me start with VA and write the node equation for that. Okay, then it's simply 1 by L. The node equation for this is the current going in this direction, which is VI minus VA integral. And that equals the current going this way, which is VA minus V divided by R. Node equation. I then write the node equation for the node V for this node here. And that is simply VA minus V divided by R is C dV dt. Okay? And that's what I have here. Two node equations. Let me summarize the result for you. Okay, and then show you a view graph where I grind through the math as to how I got the result. So here's the result I'm going to get. So if I take these two node equations, okay, and I massage some of the mathematics, I'm going to get this result. I'll show you that in a second. So by grinding through some maths and solving these two equations and expressing this in terms of V, I get a second order differential equation, d squared V, blah, blah, blah. Notice that this is different from the LC in this term. Okay, every step of the way, you can check to see if I'm lying or I'm correct. So I will indulge myself rather with a little story here. So Richard Feynman was a known smart guy, and one of the reasons that he was in the middle of talks, he was known to get up and ask some of the darndest, hardest questions. Say, aha, you have a bug in this proof here, or a bug in this equation. That's not right. And usually he would be correct. So his trick to doing this, okay, and which is one reason how he became a known smart guy, was what he would do is, as the speaker went on talking, he would kind of follow along and think of a simple initial primitive case. Okay, so in this case, I have an RLC circuit. So think of a simpler case of this. Simpler case of this is R is 0. Okay, so whenever you set R to be 0, you should get exactly what we got in the last lecture, correct? So that's what Feynman would do. He would boil this down to a simpler case, make some assumptions, and just follow along. And whenever he found a discrepancy between the math here and his simple case, he said, there's a bug there. Okay, so if you want, you can catch me that way. But so here, what Feynman would do is replace R being 0. Okay, and notice that then this equation here is exactly what we got the last time with R being 0. Okay, just remember that Feynman trick. Okay. So this is the equation we get, the second order differential equation with an R term in there. And let me just grind through the math and show you that how I got this from this. So the two node equations again. And what I do is I start by taking these two equations and differentiating this with respect to t. And this is what I get. And at the same time, I have replaced VA minus V divided by R here by this term. So I replace this with this and differentiate. Then I simply divide the whole thing by C. Then I take this expression here and write down VA is equal to this stuff here. And next, I'm going to substitute this back for VA and eliminate VA. So I take this VA, stick the sucker in here, and thereby eliminate VA and get this. And then I simplify it, and here's what I get. That's what I get. Okay, just I grind through the two equations and get that result. Okay. So like a stock record, I will repeat our mantra here, and which is that here's how we solve the equations that we run across in this course. The same 3 steps. Find the particular solution. Find the homogeneous solution. Find the total solution, and then find the constants, okay, using the initial conditions. Same step. I mean, you can recite this in your sleep. And the homogeneous solution is obtained using a further 4 steps. So let's just go through and apply this method to our equation and get the results. So VP is a particular solution, and VH is the homogeneous solution. So for the particular solution, before I go on to do that, let me set up my inputs and my state variables. So my input is going to be a step. Remember, I'm trying to draw you, take you to the point where the demo left off. So the demo had a step input. So I'm going to use a step input rising to VI. And I'm going to go with initial conditions being all zeros. So the capacitor voltage is 0, inductor current, another state variable, is also 0. And therefore, this is also fondly called the ZSR, or the zero state response, because there is only an input but 0 state. Okay? Again, remember the dashed lines here. Okay, don't say I didn't warn you. Okay. Okay, let's start with a particular solution. Okay, this is as simple as it gets. Okay, I simply write down the particular equation and stick my specific input. And remember, the solution to the particular equation is any old solution. Doesn't have to be a general solution. Any old solution that satisfies it. And I'm going to find a simple solution here. And V particular is a constant VI, works. Just remember, I mean, this has been working all along. Okay, and I'm going to keep pushing this and see if this works till the end of the course. And guess what? It will. Okay, so this is the solution. I'm done. That's my particular solution. Simple. Second, I go and do my homogeneous solution. And the homogeneous equation, remember, is the same old differential equation with the drive set to 0. Remember that sometimes this equation with the drive set to 0 is the entire equation you have to deal with in situations where you have 0 input, for example. Okay, or in other situations in which you have an impulse at the input. And the impulse simply sets up the initial conditions. Okay, like a charge in the capacitor or something like that. Okay, so we're going to blast through this 4-step method. The method simply says that 4 steps. I'm going to assume a solution in the form A e to the st. And if you think you've seen that before, yes, you have seen it many times before, and you will see it again, and again. Okay, and we need to find A and S. We want to form the characteristic equation, find the roots of the equation, and then write down the general solution to the homogeneous equation as this. Same old, same old. Okay, so let me just walk through the steps here. Step A, assume a solution of the form A e to the st. And so I substitute the A e to the st as my tentative solution into the equation. And again, let me remind you that the differential equations that we solve here are really easy, because the way you solve them is you begin by assuming you know the solution and stick it in and find out what makes it work. Right, so I'm going to stick A e to the st into this differential equation, and A comes out here. Differentiate this d squared, I get s squared down here, as here, and this simply gets stuck in down here with the 1 by LC coefficient. Okay, the next step, I begin eliminating what I can. So I eliminate the A's, and then eliminate the e to the st's, and I end up with this equation here. Okay, I end up with this equation. This is my characteristic equation. Okay, it's an equation in S. Do people remember the characteristic equation we got for the LC circuit? Remember the Feynman trick? That's right, LC. So S squared plus LC plus 1 by LC equals 0. Okay, this thing wasn't there. So all you do is simply follow the R. You just follow the R. Okay? Just imagine this is a dollar sign and kind of follow it. Okay, and you'll see what the differences are between the LC and the RLC. Okay, so this is the characteristic equation. So what I'm going to do is, much as I wrote the characteristic equation for the LC circuit by substituting omega naught squared for 1 by LC, let me do the same thing here, but introduce something for R and L as well. So what I'll do is, let me give you this canonic form. Okay, the very first second order equation I learned about when I was a kid was this one, S squared plus 2AS plus B squared or something like that. Okay, so let me write it in that form where I get 2 alpha S plus omega naught squared. So again, remember, the alpha comes about because of R. So omega naught squared is 1 by LC, and alpha is RL divided by 2. Okay, so omega naught is squared is 1 by LC, and R divided by L is equal to 2 alpha. Okay, so I'm just writing this in a simpler form so that from now on, going forward, I'm just going to deal with alphas and omega naughts. Okay, so once I get to this characteristic equation, after that, I can give you one generic way of solving it. And depending on the kind of circuit you have, a series RLC, which is what we have, or a parallel RLC, you will simply get different coefficients for the alpha term. This is going to stay the same, but this term will look different. Okay, alpha is going to look different. Okay, there's a real pattern here. And what I'm doing is simply focusing on what's important, what the differences are between the pattern you've learned in the 1 by LC, the LC situation and the RLC situation. Okay, so given this, I can now write down, so I'm just simply replacing this as my characteristic equation and dealing with alphas and omegas. Okay, I'll give you a physical significance of alpha in a little bit. You remember the physical significance of omega naught. That was the oscillation frequency. So in other words, given an inductor and capacitor, you put some charge on them, on the capacitor, and you watch it, it will oscillate. Okay, and its oscillation frequency will be 1 by square root of LC. The magnitude of the initial conditions will determine how fast, how high are the oscillations, or what the phase is in terms of when it starts. But the frequency is going to be the same. Okay, so my step 3 to solve the homogeneous equation is find the roots of the equation. So S1 and S2, and here are my roots. Okay, good old roots for a second order little s squared equation here. And finally, given that I have the roots, I can write down the general homogeneous solution. Okay, so general solution is simply A1 e to the st, S1t, A2 e to the S2t. That's it. That's the solution. Okay, this looks big and corny, but we're going to make some simplifications as we go along and show that it ends up boiling down to something cos omega t. Okay, so the math is kind of involved, but we get down to something very simple, a cosine. Okay, so hold this general solution. So from that, as step 3 of the differential equation solution, I write the total solution down, and my total solution is the sum of the particular and homogeneous, and so therefore I get this. So VI was my particular, and this term here is my homogeneous solution. Okay, now if I wasn't doing circuits and simply trying to solve this mathematically, here's what I would do. Okay, so I would find the unknowns from the initial conditions. So I know that V0 was 0, and so therefore if I substitute 0 for V0, I get this. So if I substitute 0 here, T is 0, T is 0, so simply get V1, A1, A2. And let me just blast through because I'm going to redo this differently. I is C dV dt, and so that's what I get. I substitute 0, and this is what I would get. Okay, I hurried through this. Don't worry, I'm going to do it again. So if you just do it mathematically, this is what you can solve this equation here, and these two simultaneous equations in A1 and A2, and get the coefficients, and you're done. Okay, but it doesn't give us a whole lot of insight into the behavior of these terms here. Okay, so what I'm going to do for now is kind of ignore that. Okay, ignore I did that. And instead, try to go down a path that is a little bit more intuitive. Okay. So let's stare at this expression we got for the total solution. That was the expression we got. All I did is I had alpha in there. I simply pulled out the alpha outside. So this is my total solution. V1 plus A1 is e to the minus alpha t, something else, and something else. Okay? There are three cases to consider depending on the relative values of alpha and omega naught. Okay. If alpha is greater than omega naught, so if alpha is greater than omega naught, then I get a real quantity here. Okay? So square root of a positive number, I get a real number, and that number will add up to the minus alpha, and I'm going to get a solution that will look like, oh, I'm sorry. Let me just do it a little differently. There are three situations here. One is alpha less than, greater than omega naught, alpha equals to omega naught, and alpha less than omega naught. Okay, this alpha is greater, alpha is less, alpha is equal to this term inside the square root sign. Okay? For reasons you will understand shortly, we call this the overdamped case, the underdamped case, and the critically damped case. Okay? When alpha is greater than omega naught, this term gives me a real number. Okay, and I get something as simple as this. Remember, for the series RLC circuit, alpha was R divided by 2L, remember? So if R is big, so in other words, if in my RLC circuit R is huge, okay, then I'm going to get this situation. Okay, my output voltage on the capacitor is going to look like this. Okay, a sum of two exponentials. And if I were to plot it very quickly for you, if for a VI step, we would look like this. Okay, so we would simply look like this because it's a sum of a couple of exponentials. All right? Now, alpha is positive here, remember. Alpha 1 and alpha 2 are both positive. Okay, so these two added up will give, because of this constant VI, give rise to something that increases in the following manner. Let's look at the situation where alpha is less than omega naught, where the term inside the square root sign is negative. Okay, so what I can do is pull the negative sign out and express it this way. What I'm going to do is, since alpha is less than omega naught, I'm going to reverse these two and pull out square root of minus 1 to the outside. This is what I get. So I'm just playing around with this so that whatever's in the square, under the square root sign ends up giving me a positive real number. Okay, so I pull the j outside, and this is what I get. Now let me blast through a bunch of math and end up with something very, very simple for this underdamped case. So let me define a few other terms. So I'm going to call omega naught minus alpha squared, the square root of that. I'm going to call it omega d. Okay? And here's what I get. So I've defined three things for you now: alpha, omega naught, and omega d. Okay? And I get this equation in terms of alpha and omega d. And then, remember from your good old Euler relationship, e to the j omega d is simply cosine plus a j sine. Okay, I'm just going to blast through a bunch of math, so, you know, rather quickly. So once I replace this in terms of a cosine and sine, cosine and a j sine, and then collect all the coefficients together, I get an equation of the form Vi plus some constant e to the minus alpha t cosine plus some of the constant e to the minus alpha t sine. Okay, remember the sines and cosines are coming out, but because of my r, I'm getting this funny alpha here, e to the minus alpha here. Okay, so I'm getting sums of sines and cosines, and k1 and k2 are some constants which I will need to determine from my initial conditions. So I'm going to continue on with this and keep on simplifying it, because as I promised you, I want to get to something that's just a cosine. Okay? So I want to go down this path. I'm not going to cover this case, the critically damped case. Okay? And I'll touch upon it later, but not dwell on it. Okay. So let me continue down the path of the underdamped case, and this is what we had. Continuing with the math, let's start with the initial conditions. V naught equals 0. And that gives me K1 equals minus Vi. So at V naught equals 0, t is 0. So this term goes away. The cosine becomes a 1. E to the alpha t goes away. And k1 is simply minus vi. Then I know that I0 is 0. And I is simply c dv dt. And I get this nasty expression. I substitute t equal to 0, and I get something that looks like this. I know what k1 is, and so therefore k2 is simply minus v1 alpha divided by omega naught. Okay, I've taken this expression where the unknowns k1 and k2 are to be found. I set the initial conditions down at t equal to 0, and I get k1 and k2 as follows, which gives me the following solution. So this is the solution I get, where I don't have any unknowns anymore. Remember that omega d and alpha are directly related to circuit parameters. Alpha was r divided by 2l, and omega d was square root of alpha squared minus omega naught squared, and omega naught squared was 1 by square root of LC. So I know it all now. Okay, I still have sines and cosines here, so I'm going to simplify this a little further. Oh, but before I go on to do that, let's do the Feynman trick again. And notice if, I'm still true to the LC circuit I did the last time. Remember, when R goes to 0, alpha goes to 0. Because alpha is R divided by 2L. So if alpha was 0, what happens to me? If alpha was 0, this guy goes to 1. This whole term goes to 0. Okay? And omega dt now ends up becoming omega naught. Okay? And I get this term here. Okay, I get vi minus vi cosine omega t, which is exactly what I expected in my equation. Okay? So this is the same as the LC case that I got. Okay. So let's go back to this situation and simplify it further. So if you look at Appendix B7 in your course notes, Appendix B7 is a quick tutorial on trig. And in that trig tutorial, you will see that, and you've probably seen this before too multiple times, the scale sum of sines are also sines. This is an incredibly cool fact of sinusoids. Well, if you take two sinusoids of the same frequency and you scale them up in any which way and add them up, okay, you also end up with a sinusoid. Okay? It's hard to believe, but it's true. It's an incredible property of sinusoids. Take any two sinusoids, scale them in any way you like, same frequency, add them up, you'll get a sinusoid. What that is saying is that, look, here's a sinusoid, here's a sinusoidal function, and I'm scaling them up in some manner, so I should be able to add them up and get a single, be able to express that as a single sine. And to be sure, you can. So look at the appendix. There's an expression for alpha, a1 sine x plus a2 cosine x is equal to a cosine of blah, blah, blah. Okay, this is what you get. Just simple, the math, no magic here, just math. From here, I directly get this, and look at what I have. It's absolutely unbelievable. Vt is simply Vi. There's a constant here. There's an e to the minus alpha term, and there's a cosine. Okay. Again, to pull the Feynman trick, if this alpha were to go to 0 here, then you would end up with the same expression you had for the LC situation. Okay? So let's stare at this a little while longer. There's a constant plus a minus a cosine term. So there's a sinusoid at the output, and there's an e to the minus alpha, which ends up giving you the decay you've seen before. In other words, this was to a step input, the LC circuit would give you a sinusoid. Okay? So that's what the LC circuit would do if alpha was 0. But because of this alpha term here, e to the minus alpha t, that gives rise to a damping effect. So this causes this thing to become smaller and smaller as time goes by until this term goes to 0 at t equals infinity. Okay, so this guy damps down, and so therefore you end up getting the curve that you saw like this. Okay, so a lot of 20 minutes of juggling of math to solve the second order differential equation, but what ends up is the same sinusoid, but it's damped in the following manner, such that the frequency, rather the amplitude keeps decaying until it starts off at 0 and then settles down at VI. This is exactly what you saw in the demo that we showed you earlier. The critically damped case, I'm not going to do it here. I'm going to point you to the following insight. The underdamped case looked like this. Okay, it was a sinusoid that kind of decayed out. That was the underdamped case. And then I showed you the overdamped case. The overdamped case looked like this. And as you might expect, the critically damped case is kind of in the middle and looks like this. Okay, so this is the overdamped case will look like this, underdamped like this, and the critically damped case kind of goes up and then settles down almost immediately. This is when alpha equals omega naught. Okay, I'm not going to do that. I won't do that case here, and I'll simply point you to section 13.2.3. Okay, so just to tie things together, recall this demo here that we showed you in class yesterday, and this is exactly the kind of form of the sinusoid you saw because of that input step. If you want to see a complete analysis of inverter pairs and look at the delays and so on because of that, you can look at page 170 and example 898. Okay, in the next 5 or 6 minutes, what I'd like to do is stare at the RLC circuit, and much like I showed you some intuitive methods to get the RC response, okay, what we're going to do is do the same thing for the RLC. Okay, in the RLC situation, much like the RC situation, experts don't go around writing 15 pages of differential equations and solving them each time they see an RLC circuit. Okay, they stare at it, and boom, the response pops out, the sketch pops out. Okay, so this one is going to be another one in our Bend It Like Beckham series here, and this one is in honor of Leslie Kolodziejski, and I call it Conquer It Like Kolodziejski. Okay, so again, as I said, experts don't go around solving long differential equations and spending 10 pages of notes trying to get a sinusoid. So look at the circuit, and they sketch the response. Okay, so I'm going to show you how to do that too. And what you can do is, to practice, you can go to WebSim and try out various combinations of inputs and initial conditions and sketch it. Time yourself, give yourself 30 seconds or a minute if you like, and sketch it and check it against the WebSim response. If it doesn't match, either you're wrong or there's a bug in WebSim. Okay. So what I'm going to do is the response for the critically damped and underdamped case was very easy to sketch out. You started with an initial condition, you settled at VI, and you kind of drew it like that. The interesting case is the underdamped case, and that's what I'm going to dwell on. So before we go on and I show you the intuitive method, as a first step, I would like to build some intuition. Okay? Let's stare at this response here and try to understand what's going on. So this is the response that we saw. And this fact that you see oscillations happening is also called ringing. Okay, you say that your circuit is ringing. All right? You see some interesting facts. You see that the frequency of the ringing is given by omega d. Okay, this cosine omega d, so that's the frequency omega d. So the time is 2 pi divided by omega d. Okay, so the oscillation frequency is omega d, where omega d is simply omega naught squared minus alpha squared. Once you have a big value of r, alpha becomes very small, and omega d is very commonly equal to, very close to omega naught. Okay, so omega d and omega naught very commonly are very close together. Okay, and when that happens, this frequency is directly omega naught. Alpha governs how quickly your sinusoid decays. Okay, so e to the alpha t here is the envelope that governs how quickly my sinusoid decays. Okay? And notice that each of these terms, alpha and omega naught, comes directly from my characteristic equation. Which means that once you get your characteristic equation, you really don't have to do much else. And up to now, you still have to write the differential equation to get the characteristic equation. Okay, so you still have to do some differential equation stuff. But in 2 lectures, I'm going to show you a way where you can even write down the characteristic equation by inspection. You can look at your circuit and boom, in 15 seconds or less, write down the characteristic equation. It's absolutely unbelievable. Okay? So what are the other factors that are interesting here? So of course, I need to find out the initial values. I start off at 0. This is my capacitor voltage. If I don't have a infinite spike or an impulse, my capacitor voltage tries to stay where it is and starts off at 0. And the final value is given by VI. The capacitor is a long-term open. So therefore, VI appears across the capacitor. And so in the long term, my final value is going to be VI. There's one other interesting parameter, which I'll simply define today, but dwell on about a week from today. And that's called the Q. Okay, some of you may have heard the term, oh, that's a high Q circuit. Okay, Q is an indication of how ringy the circuit is. Okay? And Q is defined as omega naught by 2 alpha. It's called the quality factor. Okay? And it turns out that Q is approximately the number of cycles of ringing. So if you have a high Q, you ring for a long time. If you have a low Q, you ring for a very short time. Okay, that's called the quality factor, defined by omega naught by 2 alpha. Notice that Q, omega naught, alpha, omega d, all of these come from the terms in the characteristic equation. Okay, we'll spend more time on Q later. Okay, so with this insight, here's how I can go about very quickly sketching out the form of the response. So here's my circuit. Okay, I want to sketch the form of the response for a step input at VI. So 0 to VI, step input here. I want to find out what happens at this point. Okay. So this is described to you in a lot more detail in section 13.8 in your course notes. So let's go through the steps. Let's do the really simple situation first. Let's also assume for fun that you are given that V0 starts out being some positive value. Okay, some V0, which is a positive number. And let's say, to make it harder on ourselves, let's say I0 starts out being some negative number. So I0 is some negative current. So the first thing I know is V0 is the capacitor voltage starts out here, which can change suddenly. And I also know that in the long term, this is an open circuit. Okay, so that this voltage VI will appear directly across the capacitor in the long term. So I get starting out at V0, ending at VI. Okay, I'm almost half the way there. I know the initial and the ending point of the curve. And then I know that somewhere in here, this must be doing some funny, there must be some funny gyrations here. Remember, I'm dealing with the underdamped case. And you can determine that from alpha and omega naught. Okay, so if alpha is less than omega naught, you know that you are in the underdamped case, and this is what you get. So let's compute all the, write the characteristic equation down. A week from today, you'll write it by inspection, but for now, you'll do it by writing a differential equation. And from the characteristic equation, you will get omega d, you get alpha, omega naught, and q. Okay? So omega d gives you the frequency of oscillations. Okay, so my frequency of oscillation is now known. From q, I know how long it rings. So I know it rings for about q cycles. Okay? So I know that ringing stops approximately here. And then I know that between the start and end point, my curve kind of looks like this. Something like this. Okay, right there, we're 95% of the way there. The only question is, I do not know if it goes like this or it goes like this. I'm not quite sure yet. It starts off going high or starts off going low, not quite clear. Okay? I also do not know what the maximum amplitude is. It turns out this is rather complicated to determine, so we won't deal with that. Just simply, give you so you can draw a rough sketch. So the question is, which way does it start? Okay? I could leave it for you to think about. Yeah, let me do that. It's given in the notes, so don't look at it. Given on this page, so don't look at it. Think about it. and think about how you can determine whether it goes up or down. It turns out that in this case, it's going to go down and then ring. Okay, see if you can figure it out for yourselves, and then we'll talk about it next week.